Hi students, next we are going to deal with the thermodynamic treatment of law of mass action. What is law of mass action? It's already discussed in the previous videos. Law of mass action is the rate at which the substance react is directly proportional to its active mass, and the rate of a chemical reaction is directly proportional to the product of the active masses of the reactant. That is the law of mass action. What is the law of chemical equilibrium, which has been derived from this same law of mass action? That is derived from the thermodynamic treatment of this law of mass action. For knowing this law of chemical equilibria, we should have an idea about what is chemical potential or activity. Activity of a substance in equilibria can be taken thermodynamic counterparts of pressure if the system considered is a gaseous. If the system is a gaseous, then we are taking the activity as such in the terms of a pressure. So even in the liquid state, then effective concentration is the we are taking as an activity. So what is chemical potential? Chemical potential is a partial molar free energy of a component in a mixture. Chemical potential is the partial molar free energy of a component in a mixture. So that is the contribution per mole of that particular component to the total free energy of the system under conditions of constant temperature and pressure. Chemical potential means it is the partial molar free energy of a component in a mixture. That is the contribution. Our component contribution per mole of that particular component to the total free energy of the system under the condition of constant temperature and pressure. So free energy we can term it as G. Those free energy of a mixture of component can be written as at a constant temperature and pressure is given by G at constant temperature and pressure will be is equal to N1 into mu1. Mu is the representation for the chemical potential. So N1 mu1 plus N2 mu2 plus etc. where N1, N2 etc. are the number of represent the respective number of moles of the component, and mu1, mu2 are the represent the respective chemical potential of that component. So activity A of the first component of mixture at constant temperature and pressure is defined as relation to its chemical potential mu I. The activity of the every component can be related with its chemical potential. So mu I will be chemical potential of ith component. Mu I will be is equal to mu I0 plus RT into ln AI. AI is the activity of that component. Mu I0 is the standard chemical potential. It is the chemical potential in its standard state at the same temperature. Okay, so next we are going to deal with the what is the law of chemical equilibrium, that is van Hoff reaction isotherm, derivation of van Hoff reaction isotherm and the law of chemical equilibrium. So for that we are considering a general reaction A into A plus B into B plus etc. gives Ln plus Mn plus etc. under any chosen condition of pressure, temperature and composition. So total free energy of the reactant consists of A moles of A and B moles of B etc. is given by, so reactant free energy will be given by G reactant will be is equal to A into mu A plus B into mu B. And for the product same we can written as G product will be is equal to L mu L plus M mu M plus etc. This is the equation 1 and this is the equation 2. So equation 1 and 2 represent the new term, and that is the chemical potential of the species, the component. At constant temperature and pressure, what is change in free energy is given by, change in free energy can be written as delta G is equal to G product minus G reactant. So this is the G product and this is the G reactant. We know that previously we saw that mu will be is equal to mu 0 plus RT ln A. So everywhere where the mu is coming, that we are representing in a standard chemical potential term. So delta G will be equal to L into mu 0 plus RT ln AL. Likewise, and elaborate the equation. And at last we can see that the common term RT ln A1, or that we are taking in a one term, and L into mu 0 plus mu, that is in the same term, or we are in one place, and same another term will be in another place. So we can rewritten as this equation is whole bracket into L into mu N plus etc. minus A into mu 0 minus plus into whole bracket RT ln A is likewise this. So since the term in the square bracket equation 6 gives the delta G0, this will be the delta G0. So we can write that delta G will be equal to delta G0, and this term we can rewritten like that, RT into ln L raised to L into AM raised to, like that. This equation is known as Van Hoff reaction isotherm. This equation is known as Van Hoff reaction isotherm. If the system is in the equilibrium, then we know that change in free energy will be equal to 0. Then putting the equilibrium activity equation 7 becomes likewise. It will be like that. 0 will be equal to delta G0 plus RT ln equilibrium. So delta G0 is equal to minus RT, and we know that this is a equilibrium constant K. So delta G0, if it is in activity, that Ka. If it is in concentration, then it will be Kc. If it is in pressure, then it will be Kp. So K is the thermodynamic equilibrium constant. K is the thermodynamic equilibrium constant. So this equation 10 is known as law of chemical equilibrium. This equation is known as law of chemical equilibrium. Since the activity of each constant is proportional to smaller constant, so we can rewritten as like this, or sometimes if it is in a pressure term, then it will be the gaseous, then we can rewritten like this. Then, so from the following equation 9 and 10, we can written as delta G0 is equal to minus RT into ln K, minus RT ln K. Delta G0 is a RT ln K. If it is in a gaseous state, then minus RT ln Kp. So here RT ln Kp na ln log like matum 2.303 into RT log Kp. So we know the value of Kp, we can calculate the delta G0 of the equation. Here in this slide, it is showing the relation between the Kp is how it is varying according to different temperature, or dependence of equilibrium constant, temperature dependence of equilibrium constant. The equation, we know this equation, delta G0 is equal to minus 2.303 RT by ln Kp. Then we know that equation delta G0 is equal to delta H0 minus T delta S. So delta G0 is equal to minus RT. So we can rewritten as ln Kp minus RT ln Kp is equal to delta H0 minus T delta S0. So RT ln Kp will be equal to minus delta H0 plus T delta S0. So we can rewritten as ln Kp is equal to minus delta H0 by RT plus delta S0 by R. So we are changing the temperature from one form to one temperature to another, then we have to integrate the value. So the second term will become 0. So it will be like this, log Kp2 by Kp1 is equal to delta S0 by 2.303 R into T2 minus T1 by T2 into T2. So while knowing this equation, we can calculate the how the temperature means equilibrium constant is depends the how it is varying according to temperature. Equilibrium constant is varying according to temperature. Thank you. In the next video, we will discuss about what is a homogeneous system, and just homogeneous system and heterogeneous system, what is meaning, and then the factors that change the state of equilibrium. state of equilibrium. We learned that equilibrium constant, how it is varying with reference to different factors. Next, we are going to state of equilibrium, and that is Le Chatelet principle and different factors which influencing the state of equilibrium, that we are going to learn in the future videos or coming videos. And so thank you very much.